Hello everybody, my name is Ethan. Welcome back to the channel where today we're going to be continuing our series on the machine learning class in Codecademy. In the previous video we learned about decision trees, which is a concept that is pretty useful. We didn't do the best covering of it. Today we're hoping to do a better covering on normalization. And we're going to have some other stuff here. That we have some stuff to go through, but it looks like we're towards the end of this supervised learning regressors, classifiers, and trees unit. After that, we will finish the featured engineering 2, feature selection methods, and then unsupervised learning algorithms. This video should not be that long. It says that it's 32 minutes left in this section, and usually we go a little bit faster than that. So let's jump right into it. Normalization. This article describes why normalization is necessary. It also demonstrates the pros and cons of min-max normalization and z-score normalization. So, why normalize? Many machine learning algorithms attempt to find trends in the data by comparing features of data points. However, there is an issue when the features are on drastically different scales. For example, consider a data set of houses. Two potential features might be the number of rooms and the total age of the house in years. A machine learning algorithm could try to predict which house would be best for you. However, when the algorithm compares the data points, the feature with the larger scale will completely dominate the other. Let's take a look at the image below. So obviously, you're not going to get a house with 100 rooms, right? And there are houses obviously with 100 rooms, but it's not the normal amount, especially when you start getting into houses that are 100 years old. When the data looks squished like that, we know we have a problem. The machine learning algorithm should realize that there's a huge difference between houses with 2 rooms and a house with 20 rooms. But right now, because 2 houses can't be 100 years apart, or can be 100 years apart, the difference in the number of rooms contribute less to the overall difference. As a more extreme example, imagine what a graph would look like if the x-axis was the cost of the house. The data would look even more squished. The difference in the number of rooms would be even less relevant because the cost of 2 houses could have a difference in thousands of dollars, right? The goal of normalization is to make every data point have the same scale, so each feature is equally important. The image below shows the same house data using min-max normalization. Typically, min-max normalization is going to squish all of your data points into a range from 0 to 1 and kind of give you an idea there. So we have years normalized, and this looks a lot better than this. We can do a lot more with this than we can with this, right? All right, min-max normalization. Min-max normalization is one of the most common ways to normalize data. For every feature, the minimum value of that feature gets transformed into a 0. The maximum value gets transformed into a 1, and every other value gets transformed into a decimal between 0 and 1. For example, if the minimum feature was 20 and the max was 40, then 30 would be transformed into about 0.5 since it's halfway between 20 and 40. The formula is as follows: value minus the minimum value divided by the maximum minus the minimum. Min-max normalization has one fairly significant downside. It does not handle outliers very well. For example, if you have 99 values between 0 and 40 and one value is 100, then the 99 values will also be transformed to a value between 0 and 0.4. That data is just squished as before. Let's take a look at the image to see how we look. Exactly, right? It's very squished right here. Not great. Obviously, when we normalize it, it's going to look a little bit better, but still we're going to be a bit squished out just because of this point. Normalizing fixed the squishing problem on the y-axis, but the x-axis is still problematic. Now, if we were to compare these points, the y-axis would dominate. The y-axis can differ by 1, but the x-axis can only differ between 0 and 0.4, again, because we just have that one at 1, right? Or the one that was all the way up at 100 when everything else is below 40. So z-score normalization. So z-score normalization is a strategy of normalizing data that avoids this outlier issue. The formula for z-score normalization below is the value minus the mean divided by the standard deviation. Hopefully you know a little bit about z-score. That's definitely helpful for this course. Here, mu is the mean value of the feature and sigma is the standard deviation of the feature. If a value is exactly equal to the mean of all values of the feature, it will be normalized to 0. If it is below the mean, it will be a negative number, and then if it's above the mean, it will be a positive number. The mean, or the size of those negative and positive numbers, is determined by the standard deviation of the original feature. If the unnormalized data has a large standard deviation, the normalized values will be closer to 0. Let's take a look at the graph below. This is the same data as before, but this time we're using z-score normalization. So we have the z-score normalization. A lot of them hover around 0, -1, just one standard deviation above and below the mean. Here, though, we can clearly see that this outlier is 5.5 standard deviations above the mean. That's obviously extremely large and a significant outlier. Now, while this data still looks squished, notice that the points are now roughly on the same scale for both features. Almost all points are between -2 and 2 on both the x-axis and y-axis. The only potential downside is the features aren't on the exact same scale. With min-max normalization, we were guaranteed to reshape both of our features to be between 0 and 1. Using z-score normalization, the x-axis now has a range from about -1.5 to 1.5, while the y-axis has a range from about -2 to 2. This is certainly better than before. The x-axis, which had previously ranged from 0 to 40, is no longer dominating the y-axis. So, review. Normalizing your data is an essential part of machine learning. You might have an amazing data set with many great features, but if you forget to normalize, one of these features might be completely dominant over the others. It's like you're throwing away almost all the information. Normalizing solves this problem. In the article, you learned the following techniques: min-max normalization and z-score normalization. Moving on here. I believe we have a couple more articles that we are going to cover here. This next one's about training, validation, and test data sets. This is a lot of recap, basically, of this section. So I'll say this is kind of a recap video of all of the previous stuff that we have covered. Obviously, it's not an in-depth recap, but it's going to give us a good idea of what we actually covered. Training, validation, and test data sets. This article teaches the importance of splitting a data set into training, validation, and test sets. Supervised machine learning models have the potential to learn patterns from labeled data sets and make predictions. But how do we know if the predictions our models are making are even useful? After all, it is possible that every prediction our email spam classifier makes is actually wrong, or that housing price prediction our regression model makes is orders of magnitude off. Luckily, we can leverage the fact that supervised machine learning models require a dataset of pre-labeled observations to help us determine the performance of our model. To do so, we'll have to split our labeled dataset into 3 chunks: a training, validation, or test, or holdout set. Training, validation, test split. Before we can even talk about writing the code we will use to fit our machine learning model to the data, we must perform a split of our dataset to create a training test, validation test, or set, and test set. The training set is the data that the model will learn how to make predictions from. Learning looks different depending on which algorithm we're using. With linear regression, the observations in the training set are used to fit the parameters of the line of best fit. For choose different models classification, the observations in the training set are used to fit the parameters being fit. The validation set is that will be used to during the training phase to evaluate the interim performance of the model, guide the tuning of hyperparameters, and assist in other model improvement capacities, for example, feature selection. Some common metrics used to calculate the performance of machine learning models are accuracy, recall, precision, and then that F1 score. The metric we choose will vary depending on a particular use case. The test set is the data that will determine the performance of our final model, so we can estimate how our model will fare in the real world. To avoid introducing any bias to the final measurements of performance, we do not want a test set anywhere near the model training or tuning processes. That is why the test set is often referred to as the holdout set. All right, evaluating the model here. During model fitting, both features X and true labels Y of the training set, X-train and Y-train, are used to learn. When evaluating the performance of the model with the validation set, X-val and Y-val, or test, X-test and Y-test set, we are going to temporarily pretend like we don't know the true label of every observation. If we use the observation features in our validation, X-val or X-test sets such as inputs to the training model, we can receive a prediction as output of each observation, Y prediction. We can now compare each of the true labels, Y-val or Y-test, with each of the predicted labels, Y-pred, and we'll get a quantitative evaluation of the performance of the model, right here. How to split. Figuring out how to split, how much of our data should be split into training, validation, and test sets is a tricky question, and there's no simple answer. If our training set is too small, then the model might not have enough data to effectively learn. On the other hand, if our validation and test sets are too small, the performance metrics could have a large variance. In general, putting 70% of the data into a training set, 15% of the data into each of the validation and test sets is a good place to start. All right, n-fold cross-validation. Sometimes our data set is so small that splitting into training, validation, and test sets that are appropriate sizes is unfeasible. A potential solution to perform n-fold cross-validation a potential solution is to perform n-fold cross-validation. While we still first split the data set into a training and test set, we are going to further split the training set into n chunks in each iteration or fold, and -1 of the chunks are treated as the training set, and 1 of the chunks is treated as the validation set over which the evaluation metrics are calculated. So we've got fold 1, fold 2, all the way to fold 10. And then it will test the validation set based on which fold we're on. The process is repeated n times, cycling through each chunk, acting as a validation set and evaluation metrics for each of the fold are average. For this example, in a 10-fold cross-validation, we'll make the validation set first 10% of the training data set and calculate then we'll make it the second 10%, so on and so forth. We'll get a better sense of how our model does on average. Finally, we're going to go into the confusion matrix, something that we had already kind of previously looked at. Evaluation metrics. Oh, so these are the evaluation metrics for classification. This is definitely something that we have already covered, but it's good to do a little recap here. When creating a machine learning algorithm capable of making predictions, an important step in the process is to measure the model's predictive power. In this lesson, we'll learn how to calculate some of the more common evaluation metrics for classification problems. Remember, in order to calculate these statistics, we need to split our data into training, validation, and test set before we start fitting our model. Let's say we are fitting a machine learning model to try and predict whether an email is spam or not. We can pass the features of our evaluation set through the trained model, get an output list of the predictions our model makes. We then compare each of these predictions to the actual labels. There are possible categories that they can fall under: true positive, true negative, false positive, false negative. One common way to visualize these values is in a confusion matrix. In a confusion matrix, the prediction classes are represented as columns and the actual classes are represented as rows. Let's calculate the number of true positives, false positives, true negatives, and false negatives from an evaluation data of classification algorithm. Then we'll construct the confusion matrix. So we've given 2 ordered lists here, actual and predicted. It says actual represents the true labels. Each one in the list represents an email that is spam. Each 0 represents that not spam. Predicted represents the classifications that the machine learning algorithm returned. Create 4 variables to store the results. They should be called true positives. For right now, I'm going to just set them all equal to 0. Oh my. True positives. True negatives, false positives, and then we'll have also false negatives. False positives, I can spell. Loop through each of the predictions in the list and add 1 to true positives every time the algorithm found a true positive. A true positive is when the actual label and the classifier predicted are both 1. So I'll do for index in range length of actual. We are going to do if actual at the index is equal to predicted at the index. We're going to do true positives every time the algorithm found a true positive. Oh, I see. So we'll do this instead. If actual positive is equal to 1, and then we can put the AND operator, which is this, and we'll say that predicted is equal to 1. Then we'll say true positives plus equal 1. Now, inside of the loop, count the number of true negatives, false positives, and false negatives. So, true negatives would be, we'll do another elif. So we'll say if idx is equal to 0 and predicted idx is equal to 0, we'll do true negatives plus equals 1. And I'm going to make another elif statement. Now, the other ones are a little bit more tricky. False positives, which means that our actual predicted to 0, and then our predicted a 1. So I'll say elif actual with idx. So we're saying this is the false positive, which means we predicted that it was going to be a 1. In fact, it was a 0. We're going to say that actual has to be a 0, and predicted idx is equal to 1. Then we'll do false positive. False positives plus equals 1. And finally, the last elif statement, actual idx is equal to 1, while also predicted idx is equal to 0. So in that case, we're going to say false negatives plus equals 1. So I think I might have gotten them mixed up. A false positive is when predicted is equal to 1 and actual is equal to 0. Okay, so a true negative is when they're both 0. True negatives plus equal 1 when actual is equal to 0 and predicted is equal to 0. False positive is when predicted is equal to 1, but actual is equal to 0. And then actual is equal to 1. This is interesting. How did they do it? They just replaced, they used the and character. I don't think that would make a difference. And I just used the value of actual instead of the value of predicted. I mean, this shouldn't work. Wow. What? Why does that work? All right, outside of the loop, print all of them. Let's just keep going. I'll look into that after, but if we print true positives, true negatives, we'll print false positives and false negatives. 3, 0, 3, 4. We've already imported the confusion matrix, create a variable called confusion matrix. So we'll say conf matrix is equal to confusion matrix with the values of actual and predicted, and then print it. It wants me to do. Yep, looks very similar to what we had here. Awesome. All right, accuracy. One method for determining the effectiveness of classification algorithm is by measuring its accuracy statistic. Accuracy is calculated by defining the total number of correctly classified predictions, true and positives and true negatives, dividing it by the total number of predictions. So accuracy is defined by true positive plus true negative divided by everything else. So we're going to calculate the accuracy of it. To do that, we'll just make a variable called accuracy, and we'll set that equal to the true positives plus the true negatives. And I am just going to wrap that quickly in a thing and then divide by everything else. So I'm also going to get a new parenthesis going. I'm going to just quickly copy and paste this, but then also add false negatives and false positives. I think I used a comma instead of actually doing the correct operation, which would just be plus. And then they want me to print accuracy. So it says my accuracy is 30%. Oh, that actually is pretty smart if you just divide it by length predicted. That's actually a little bit smart. All right, recall. Accuracy can be a misleading statistic depending on our data and the problem we're trying to solve. Consider a model predicting spam in the inboxes of a top secret government employees who never use their work emails for online shopping or logging on their favorite gaming apps. We can write a pretty simple and accurate classifier that always predicts false. The email is not spam. This classifier will be incredibly accurate since there is hardly ever any spam emails sent to those top secret emails. But this classifier will never be able to find the information we're actually interested in when there is spam. In this situation, a helpful statistic to consider is recall. In our example, recall measures the ratio of correct spam predictions that our classifier found to the total number of spam emails. Recall is defined by true positives divided by true positives plus false negatives. So correct spam predictions to the total number of spam emails. I see. Recall is the ratio of correct positive predictions made by the model to all positives. For example, or for the spam classifier, this would be the number of correctly labeled spam emails divided by. So let's calculate recall. We can do this by just following this. We'll do true positives divided by the sum of true positives and false negatives. And then we'll print recall. Line 20. Oh, that was weird. 42%. It's looking like that's something. Precision. So unfortunately, recall isn't the perfect statistic either. Spoiler, there are no perfect statistics. For example, we could create a spam email classifier that always returns true. The email is spam. The particular classifier would have low accuracy, but the recall would be 1 because it would be able to accurately find every spam email. In this situation, a helpful statistic to understand is precision. In our email spam classification example, precision is the ratio of correct spam email predictions to the total number of spam predictions. Precision is defined as true positives divided by true positives and false positives. So I assume we're just going to kind of continue what we've been doing, create a variable called precision, and set it equal to true positives divided by the sum of true positives and plus false positives. F1 score. It is often useful to consider both the precision and recall when attempting to describe effectiveness of a model. F1 score combines the both precision and recall into one statistic. It's defined as this. We can just go ahead here and create the F1 score. We'll call it F1, set it equal to 2. I'm actually going to start with parentheses 2 times precision times recall. So first I'm going to make a precision and recall variable. if we remember here, precision is equal to true positives divided by the sum of true positives plus false positives. And then we have recall, which I'm hoping is true positives divided by the sum of true positives. Can't spell positive today. Plus false negatives. Now we can do 2 times precision times recall, and then we'll divide that by precision plus recall. And we did get it correct, which is awesome, but we want to print f_1. We get that 46%. Cool. All right, review. There is no perfect metric. The decision to use accuracy, precision, recall, and F1 score or other metric not covered in this lesson ultimately comes down to the specific context of the classification problem. Scikit-learn has some interesting stuff. In Python's scikit-learn library has functions that help you create. Call accuracy score using the correct parameters. So we can do, if we print accuracy score on actual and predicted, what happens? Cool. We can do the same thing with by printing recall score with actual and predicted. And then obviously we can just go down the line here and with what am I doing here? Actual and predicted. Finally, the F1 score with actual and predicted. Prints them all out here. Very nice. So we do have a bit of a test here, and I assume, oh, actually, just after this test, there will be no project. So false positive when a label is a true and the prediction is a, so it's obviously not 1 and 1 or 0 and 0 because it's false. But if we look here, we think a false positive is when we actually have a 0 and the prediction is a 1, right? That makes sense. If the true labels of your data are 1, 0, 1, 1, and the prediction classifiers are 1, 1, 1, then the prediction at index 3, which is this one right here, 1, we predicted a 0 even though it was a 1, so that would be a false negative. All right. Given the following values, what is the recall of the classifier? So the recall is the true positives divided by the true positives plus the negatives. So 2 divided by 5. Right? Am I doing that right? 40% is what I would have said, but oh no, I'm saying true negatives, false negatives. So 2 plus 6, so it would be 2 over 6, so it would be 1 over 3, 1/3. My bad. In the image below, the circle with the solid line represents the true labels of a point. The point that falls within the circle has a label 1. And points outside the circle have a label of 0. The circle that with the dotted line represents the classification's guess. If the point is inside the dotted circle, it has been classified 1. Otherwise, it's classified 0. What is the equation for accuracy? Accuracy is defined by the true positives and true negatives divided by everything else. So I do like divided by ABCD, but that's every single option. It's saying that the point with this solid line, which is A here, represents the true label of points, and a point that falls in this in the circle has a label of 1, and points outside the circle have a label of 0. Circle with the dotted line represents the guess. If the point is in the dotted circle, it has been classified as 1, otherwise 0. So B plus D, yeah. True positives plus true negatives. Right. What are the parameters of sklearn's F1 score function? A list of true labels followed by a list of predictions. Why is the F1 score calculated using the harmonic mean? I didn't actually read this part, so that was a bit of my... harmonic mean makes the F1 score low when the precision or recall is low. Well, there you go. More you know. Precision is defined as the relevant number of items selected out of all relevant items. Not all items. Not all classification. Oh, it's out of all selected items. We might have to redo. Oh boy, gosh dang it. For recall, it's true predictions. So B divided by B, it should be B divided by B plus oh no, we're gonna have to redo it now. I have to retake it. That's so sad, you guys. Oh my god, this one's gonna suck too. False positive. Number 3 index is a false negative. This was the 0.33, if I remember it correctly. B plus D over A, B, C, D. A list of true labels followed by predictions. Why is the F1 score calculated? That's why precision is defined by that. And then it's going to be, for this one, if we look at it one more time, a little bit closer, recall is defined by true positives, right? So our guess would be B. It has to be B over something, right? True positives divided by true positive minus or plus. True positives divided by true positives plus false and negatives. B represents the true positives and A represents the false and negatives. Somehow that's why. Okay. That's going to be doing it for this video. I want to thank you all so much for watching. In the next video, we're going to continue on with the new section. We learned a lot. We are still very little through this course, which I'm obviously excited about, but that was the biggest first section, right? This section, only 4 dots, but there was so much. If you actually go into it, you see there's actually a lot that we ended up covering. In the next episode, we're going to be doing Feature Engineering 2, Feature Selection Methods. If you did enjoy this video, please be sure to leave a like, subscribe, and I'll see you in the next one. Peace out.